Hey, welcome back. Thanks for coming in Friday afternoon. It's cold out. It's almost the weekend. But we're here. So last part of this, or wait, actually, did we finish up part C?
I don't think so.
What was left?
Find out.
Let's come down here. Let's save this. Oh yeah, it's Friday the 13th too. Ooh, spooky. Yeah, where did we leave off? I think the last thing we were just talking about was like trying to choose what your stopper would be, like what that normal force was. Was there anything left over? Like, did anyone leave not knowing where to go from there? That was from Wednesday, trying to figure out how friction would actually stop this thing as it's coming down. Let me check in and see where people are at. Any issues? Any issues like figuring out how or when it's gonna stop?
We just had acceleration zero, not find distance, but everything else is studying and figure out how many force we have.
What kind?
Or like how much.
Oh, right, yeah. Yeah, do you know like how to find what you want for it? Okay. Alright, we can, delta x is 0.
No.
Oh, okay. Let's say a is 0.
I would use that.
Okay. You don't have to. If a is 0, then it will be a constant c. It won't keep accelerating, but if it came in at 3 meters per second, it would just be another thing at 3 meters per second all the time. Okay. I don't know. What is that? What you want to do? Well, that one doesn't have time in it. So it keeps this. So what do you want to do? That's why I'm asking. Are you stuck? Is it done? Is it obvious? Or is it okay. No, they should be accurate. Yes. this one has variation. The distance that it moves is up to you. How much you want to go. So we found some limiting cases, if it's 0, then it doesn't slow down at all. If it's infinite, then it immediately starts to the halfway point, sort of like if there's no acceleration, then the velocity is constant. So if we wanted to stop, it should be more than it wasn't.
All right, so questions that came up specifically for this part, like part C, was like, can we just choose any numbers, like any normal force or any distance? And as long as you're clear with what engineering decisions you're making, then it's okay to do that. Like it's an engineering problem, so not everything is laid out for you of like a perfect one solution thing. So if your goal is to minimize the impulse, like the force felt during that stopping time, then you'd want as small of an acceleration as possible, right? So then delta t gets really big, f gets really small, and maybe that's your goal for this, and that's what. So you'll compare that. If that's your goal, then you would compare what is the force, like average force for the other two methods too. And then you have a comparison that way. Or maybe you're trying to stop this thing in as short a distance as possible, so you want n to be really big, acceleration, now this F force is really big, but delta t is really small. And then again, you could compare that to the other two methods, like what were the delta t's in those two methods. Sound good? Follow-up questions from that? Nothing yet? Everyone's just too excited. They're like, I can't wait to do more math and get through this. Okay, so then come back to, then the other thing was more of like a broad question of what's expected here? Like, what are we supposed to do with this case problem? So it's an engineering problem where we have 3 different proposed stoppers. So you should be laying out like, what is the free body diagram that you're using for all 3? What are the differential equations for all 3? What are the solutions? And then the final, so that's sort of like introduction and methods. It's like that. And it's not a big long report, like we're not trying to write a technical report on this, but a short description of like why. Like one thing that came up with B was like, is there buoyancy? So if you're going to include buoyancy, like how much? Why are you doing that? Is there a benefit to it? Like just here's a buoyancy force. This is what I'm approximating it as. And then the final conclusion, like, is whenever you're comparing the 3 methods, there's some kind of graphs to show like, hey, these 3 stopped this thing or slowed it down. This was, here's position versus time, or velocity versus time, or position versus velocity, like something to kind of wrap that up. And then you can compare or contrast of like, all 3 of them did the same thing with this, but each one had pluses and minuses. Follow-up questions? No questions? Yeah, there's got
I got one or two. So going back to part C, did you give a coefficient of kinetic friction for us to, like a set one to use?
that one. So the given coefficient is 0.5. That one's just a fixed value.
Also, could you show us just like an example graph of, I guess, what it would look like, part C?
Yeah.
And look at that.
Did we take a look at this last time? Of like, this was us, right? Plotting spring versus damped motion. Okay, so then, no?
Look at both graphs, but I don't think we plotted them together. We also didn't look at C yet.
Yeah, so we haven't looked at C in this case. So right now I have both of them. The spring, like what happens when it hits the spring, it goes down, and here, up is down is up, because we said positive was moving down. So it goes down to maybe 12 centimeters and then bounces back up to 8 centimeters. And again, based on my free body diagram, it's once it hits the spring, it's kind of stuck to it. And that's just based on the model that we built with our free body diagram. Versus the, as it goes into the fluid, it comes in at 3 meters per second, and then quickly by like 0.1 seconds, now it's moving at a constant speed and just keeps going in. So then let's add the last one where we have What acceleration did we want to use here? Did anyone pick, like, this is how fast, this is what my normal force is, this is the acceleration? No. Leave that to your CEO of like, they know what acceleration should be. It's like, no, they hired you to pick it. This is your job. Pick a number. What do you think? How about 3 meters per second per second? What would that do for us? Why would I choose 3?
Because our velocity is 3 meters per second.
Yeah. So if we're
So 0 in a second.
it'll in 1 second we would have 0 meters per second. So the braking would take 1 second. So we could try that, see how it works. And then I could solve for, if that's my chosen parameter, like I want it to stop in 1 second, I need an A of 3 or 3.1, right? Because we're moving 3.1 when we first hit it. How does this look? Yeah. The y-axis is like distance into the stopper. So if it takes a whole second to slow down from 3 to 0, I'm gonna be almost, what is that, 5 feet into my stopper. So I need 5 feet of run out of like rubber stopper built into this. And again, maybe that's okay, but it's a lot. It's a big lot, especially compared to like the spring or even the damper looks like it stopped at that point compared to those rubber stoppers. And this is really like, this is why you plot it, is because if you're making these choices without even thinking about like what makes sense, right now we can see like, wow, that's not nearly as effective as even just a spring, even though the spring is a little bouncy. So we can increase it, right? If we want it to stop faster. If we want it to be like 0.1, we could say that it's like 30, right? Just make it like. Now we have another weird thing happening. What happened there? Yeah, it starts going back. It starts going back up. But why is that what friction does? It'll like push it back up out of our stopper? No? Why not?
It won't overpower gravity.
It won't overpower gravity. So it has to keep falling? Is that right? It won't overpower gravity. Why won't it overpower gravity? Or maybe you're thinking about it differently.
It only acts as the object is moving once it stops moving.
Yeah, it's only true, like our free body diagram is only true until our velocity hits 0. So once that happens, then it's gotta just stop. So really it's a parabola. When it hits the max of our parabola, it should stay at that max point. So I'll do the lazy method of doing it. X. So rather than like solving for like when does velocity equal 0 and then say like, okay, from there, I'll find what position it was. I just said, all right, what's the maximum value? When does it happen? And when that's the case, everything after that point in time is all equal to that max value. Looking better, right? At least compared to the other two methods. Like if we're trying to do something similar to a spring or this like damper. Yeah.
Can you scroll to the code real quick?
Yeah. Yeah, and this code, if you want this, I can share it out. Like we could put it into, I don't know, wherever, on Husky CT or something. Yeah, that's totally fine. Because it's kind of hard to read, like small print like that. But you could also, like if you use Excel or MATLAB, plotting those is, you can use those too. Because I'm just grabbing, I'm just taking like the solutions to my differential equations to compare them here. Like 3.1. V0 times t minus that 1/2 at squared. All right, so let's say this is my gold standard. I'm like, all right, group, I did it. I plotted everything, and this is the result. What does this mean? Is it good? Is it bad? Is one good? The other is bad? Does each one have? Is there anything that is similar between the three methods? And really, I should label these, right? Like, but just so we have like a reference, like more down is bigger number. So what do you think? We have something here. What do we have to say about it as the engineers? Yeah.
Friction stopper is the only one that actually stops.
The only one that actually stops it is friction. Okay, yeah, that's true. I mean, it stops lots of times with the spring. It comes to a stop. But yeah, it does keep going. That's true.
I just wanted to go back to the spring real quick. Did we plot that so that it was just going to be a constant sine or cosine wave, or was that going to eventually decay?
This one, at least from our free body diagram, the one that we had worked on, it was all yeah, and this is the important part about like when you're presenting this of like, that's why the free body diagram is so important. If you want to say that this thing is decaying, then there should be a force that's taking away energy from that spring. So in our case, we only had gravity we had gravity, we had spring force, then we have like kinetic energy if you think about it like from energy conservation. So gravity's conservative, springs are conservative, and then kinetic energy, we're not losing any throughout that motion. Yeah, so in this simplified spring mass gravity model, we're never losing amplitude. W for wind or what? Some things for like comparison. Now we have three solutions.
How does their snapper and assertions that was
Yeah.
This is what it is.
Okay.
I always thought the friction would be like just actually.
Stops. Yeah, actually bring it to a stop. Yeah. It's the only one that stops acting when it stops.
Friction never stops.
Yeah, their goal is to go whichever option stops it first, or whichever option stops it.
So the goal is that you're comparing three different stopping mechanisms. So like you could report, like, hey, friction is the only one that actually stops it. So maybe that's the most important, right? Or you could say the spring and the damper have benefits, but maybe they need to be like one system, combine them so that the spring keeps it from disappearing, but the damper actually brings it to a stop. And that's typical, you're going to try to like cushion the fall and use a spring plus the damper. Oh, he's easy to control. Yeah, okay. That one is pretty easy to control, because if you change something falling into a really good, when you change the opening, the bigger the opening, less damping. The smaller the opening, more damping. It's not like we could change that to E. Same with spring. We could use a different spring instead of. Yeah, because I'm given a value. In this case, it's not a damp spring. What do you mean by friction? Okay. Yeah, but that would require the that would be a zero. But this one's perfect. This one is for spring floating.
I'm not going, but I'm not going to switch. Let's just go there. Just to go.
So like in this case, I was kind of, rather than figure out what n is, so the solution is based on a. So, alright, a is 3, because we picked 4, is alright, make it 30, it's higher, so then I would say third is 90. So it would be like 30, 21, something. Yeah, if you choose one, then the other one is picked, basically, yeah. So it's a minor design choice. Choose one or the other, but I can't choose both. I can't say it's 30, but also this is choice. Yeah, yeah. That's why I was trying to figure it out, is to see if you can go out.
So is that what you also did here? Like basically, you mentioned also English. So is this also what you chose?
I didn't choose that one because it's dropped half a year. Yeah. It's too quiet. Are there? Does it already, do you feel like it's already done? Or no clue where to go next? Do you have clue to go next? Like where you're headed? What's next? Yeah? Not much?
somewhere in between.
What?
All right, so if you know where, oh, sorry, go ahead.
What defines done for this problem?
I mean, once you have your free body diagrams, the solution to those differential equations that come from free body diagram, and then some kind of graph where you can make a comparison, then it's up to you to say like, okay, that's enough. Like this is enough to say this is the difference or the similarities between the three. So what's next? Who has an idea of what they're doing next? Anyone here?
Probably is spring damping, because
Oh, try spring and damper together? Oh, so make a whole different solution? Okay, could try that. You don't have to. You're not required to like add more differential equations to the project, to like this little case problem. What else? What else are people doing to like wrap up, finish this off? This is the time to like either ask how to do it or try it, like do it and then see what you run into.
One small thing is that we didn't do, I mean, we did figure it out, but also did we write out the differential equations for the damper? For the friction?
So for case B,
I meant for the friction, I'm sorry.
oh, for C?
Yes.
C, what we said was there was like a force of friction, some kind of normal, and then some mg, and all that was like our acceleration going down. And then from there, because n had to equal n, and we're assuming that it's not like changing, like we're not like increasing the force, then force of friction is constant, mg is constant, so a is some constant value. And then we can use like, oh, I'm covering up. If you can get to like a free body diagram where it's constant forces applied, then the kinematic equations, kinematic like solutions all work out. Yeah.
why is the net MA pointing downwards for case C?
It was pointing down for A2. You can choose whatever you want, but you have to be consistent. And if I switch, yeah, if I try to say like MA is pointing up here, then really I have to say that the force of the spring is down, because I'm saying that a positive X is up, so a positive X displacement on a spring would be stretching, so it should pull it back down. So your kinetic diagram is choosing what is the coordinate system here. cool. Good question. Good clarifying. Yeah, and this is time to like just wrap it up. I mean, if we can finish today, great. If not, then I forget when due date is, but next week sometime, right? Yeah. Yeah.
So should all the differential equations be modeling on the position with respect to time?
So the differential equations are always and I'm giving like a general answer here. Like if I have 4 forces acting on something and I'm not saying it has to move in a given direction, then I would have differential equations for both x and y displacement. But overall, it's going to be like x double dot and y double dot. All those components will be some function of x. They could be x dot and time, y. I mean, really, it could be. But if it's like nice and separable, then you have these functions where you have like x dot and time. So whenever you get a solution to that differential equation, usually the solution is x of t. And then from there, you could use x dot to say this is the velocity. And that's kind of the approach that we took was, okay, here's my differential equation. I know what the initial values are, so I'm going to plug in what x of t should be to solve that second order differential equation. Yeah.
Just clarify one more time, what exactly we're submitting for this assignment?
So the we need free body diagrams, we need kinetic diagrams. That one's just you can't say you have a model without that initial kind of setup. Then from those free body diagrams, kinetic diagrams, that cements, like whatever you put in your free body diagram, that is your differential equation. And then there should be some solution to that differential equation. And then the final part is kind of wrapping up of like, you can compare the methods, contrast the methods, and make some kind of conclusion. kind of the same question of like, why? Why did you do this? I know like we did it together, and maybe you were just following along with like, all right, I'm just gonna write this down. Hopefully it comes in handy, but there's gotta be a reason for it. Like engineers, we do these kind of models. Sometimes they get way more complicated. We start using like multi-body dynamic simulations and FEA and CFD, but why go through all that effort? Like we could have just built the thing and tried it, but instead we're like trying to model it and make some kind of conclusion there. How's that for deliverable? Doable deliverable? Deliverable? Doable? Cool. All right. Thanks a lot. Have a good weekend. Happy Valentine's Day Eve, but tomorrow. Happy Valentine's.